Hello everyone. In this lecture, I'm going to derive the acceleration in fluids in Eulerian field as well as Lagrangian acceleration. So, and after that, we are going to talk about again these control volumes. What is the implications of large and small control volumes in fluids? And after that, we will drive the pressure hydrostatic equation using a small control volume. Okay, so let's get started. First, I want to talk about a particle and start the analysis with a Lagrangian acceleration, and then we can go to an Eulerian field and see how they are related to each other in terms of formulation. So we talked about Eulerian and Lagrangian approaches in the last lecture. So just to give you a brief overview, a Lagrangian approach is the approach where we follow a fluid particle, and the Eulerian approach is an approach in which we have a fixed position in space and we look at a control volume and a fixed control volume in space and write the equations as a field for that control volume rather than any fluid particle. Okay. So if we are in a Lagrangian framework, so the velocity vector of a particle, we can write it as if it varies as a function of space, which is x, y, z, and time, right? So at each space, at each position, the velocity varies, and also as a function of time. So I can write this velocity vector in three components. It has three components: one in the x direction, which I call it ui, one in the one in the y direction, which I call it v, and then y in the z direction, which I call it w. Okay, so we have, if this is our let me write it here. If this is our coordinate system, x, y, z, we can have velocities in these three directions, which is I, J, W. Okay, and I can just decompose them as this. And now if I want to see the change of these total velocity, or the total change of the velocity vector, total change, I can write it as a function of the change with respect to each of these variables. So first is partial v over partial t times delta t. So how much it changes with time, I can write it as this. How much the velocity changes in x direction, so the total velocity over partial v partial x times delta x, plus partial v partial y times delta y, plus partial v partial z times delta z. Okay, so I can write the total change of velocity in terms of each of these variables that it is dependent on. Okay, and now let's just divide all these by delta t, and so what I'm gonna get is delta v over delta t equals to partial v over partial t plus partial v over partial x times delta x over delta t, and similar to that we have partial v over partial y delta y over delta t plus partial v over partial z times delta z over delta t. Okay, and now let's take the limit where delta t goes to 0 of delta v over delta t. This is gonna give us what? If you remember from your calculus, this is just the definition of derivative, right? So as the delta t goes to 0, and then you have the total change of velocity, or delta v over delta t, this just equals, based on the definition of differentiation or derivative, to the derivative of d with respect to t, so the total derivative dv over dt, which is gonna equal to partial v over partial t plus partial v over partial x. And now if you take the derivative of this term with respect to t, you are also gonna get du over dx over dt, which is the derivative, which equals to the velocity, right, in the x direction, which I have it here. So I just substitute it here. So let me write this down. So this is going to be u, which is what? Which is actually dx over dt. And then you have the rest of the terms similarly. So what I'm going to get is this dv over dt equals to dv over dt equals to partial v over partial t plus u partial v over partial x plus v partial v, the vector v, over partial u plus w partial v over partial z. So this is what I'm gonna get, and we call this term as total derivative, or sometimes we call it material derivative. And this term is called local or partial derivative. And these terms are called convective rate of change. And the reason is because they are actually the acceleration due to convection in space. And this term is actually rate of change of v following fluid particle in Eulerian field. So what does this mean? So this means if you have a, say, Eulerian field, something like this, let's say You have a control volume. This term is showing how much of your velocity changes within that control volume with time. And these terms show and represent or denote how much your rate of change of V following this fluid particle in this Eulerian field. Okay? So if you have a steady flow, meaning that if you have a steady flow in a steady flows, this dV over partial V over partial T is 0. It means we have no change in the partial derivative of V with respect to time. But this doesn't mean that we don't have any total derivative or total acceleration. The acceleration could be due to changes in space. For example, you might have a compression here in a channel or expansion later on, like you can have something like this. So an expansion here. So the flow might be steady, meaning that the initial V is not changing, like here. Let me draw it here. So you might have a flow where you might have an expansion here, you might have a compression here. So the velocity field could be steady, meaning that this V is not a function of time. The initial V, the entering V is not a function of time, but as this velocity goes into this domain, it can experience some acceleration here. So you might have some acceleration here. And some deceleration here. And the reason is clear because of continuity equation. You have more fluid here, so in order to have the same mass flux, the velocity has to accelerate here. So you have the same mass flux as it enters here. And then here it has to decelerate, so the velocity needs to kind of decrease in order to have the same mass flux throughout this channel. Okay, so although we can have this convective rate of change is not necessarily 0, so we have a total derivative, derivative that is not 0, so dV over dt is not 0, but the partial V over partial T is 0. So this is actually the meaning of a steady flow. So when we say a steady flow, it means partial V over partial T is 0, and this doesn't mean that dV over dt is not necessarily 0. Not necessarily 0. Okay. So let me write this this term again. So we have for this, we can also write this using the divergence notation. This term. So in the divergence notation, let me write this down. You can write this as partial V, dV over dt equals to partial V over partial T plus v dot grad v. So it's just writing this term in terms of some mathematical operators, and I'm going to talk about them a little bit later. So this term, we call this as Lagrangian acceleration. And this one as Eulerian acceleration. And this one is convective acceleration. So Lagrangian acceleration means that the acceleration that you are following the fluid particle. So this is what you have usually done in your physics. So this is, for example, it's gonna be your acceleration. So if you multiply it by m, then you are gonna get the force, right? So this is what you have in physics, in Newtonian physics, right? If you multiply this by mass, you are gonna get the force on that fluid particle. And this equals to the field description of the acceleration, where we have partial E over partial t plus v dot grad v, which is the convective acceleration. And v dot grad v is just these terms, where we write it in terms of these mathematical operators. So let me talk a little bit more about this steady flow concept. So just add one more note that d over dt is material derivative when you follow a particle in the flow. For example, acceleration of a twig in water, d over dt can speed up and slow down so speed up at some points, speed up at some points, and slow down at other points. So for example, if you have here your rho over rho, your partial over partial t is 0, but as the flow, this flow goes here, it will kind of speed up here, and then when you have this extension, that twig, say you have a twig here, let me just show the streamline of that. You follow a twig or like a fluid particle here. So locally, if you look at that, it might have some acceleration here and then deceleration here, right? So this d over dt term is not zero, although the partial over partial t is zero for this control volume, meaning that the partial derivative with respect to time is zero. And this d over dt, we call it material derivative or Lagrangian derivative, meaning that it's the derivative that you follow the fluid particle. Okay, so let me say what is this v dot grad v, just as a side note for those who might have forgotten that. So note v dot grad is not necessarily the divergence of v. So this is grad dot v. So v dot grad is not necessarily grad dot v. So let's see what is the difference between them. So the right one, we call it divergence, and the left one is just the dot product between the velocity and the grad vector. So v is a vector, velocity vector, which has u, v, and w components, right? This is how we define it. And dot means the inner product with grad. So what is grad? Is partial over partial x, partial over partial y, and partial over partial z. And how about this one? This is, we have first the grad, which is partial over partial x, partial over partial y, and partial over partial z, dot, which is the inner product, with the velocity vector, which is u, v, w. So let's see what is the inner product of these, what is the difference. So the first one is going to give me u times partial over partial x plus v times partial over partial y plus w times partial over partial z. How about this one? This one gives me partial u over partial x plus partial v over partial y plus partial w over partial z. Okay, so these two are not equal to each other. And so here we have v dot grad v. So you need to have, you will just add a v vector here and just compare this with this. So let me copy it here. This is exactly this term, right? So these are not equal with each other. So you should be careful that you don't use them instead of each other and be confused about that. So you should never write v dot grad v. This doesn't equal to grad v divergence of v times v. Okay, so these never equal with each other. So this is what is in the equation, and we have it here. So this was just a short note about this mathematical operator that we used. So in the next part, I'm going to talk about the large CVs versus small CVs and drive the pressure hydrostatic equation using a small CV.